Good morning, everyone. My name is Chandra from the Faculty of Information Technology at the Industrial University of Ho Chi Minh City. Today, I will present our work on using AI and IoT to monitor the quality of cruciferous vegetables crops like cabbage, broccoli, to help farmers detect disease early and manage their farms more sustainably. Let me start with the problem we are trying to solve. Cruciferous vegetables are very important to Vietnam agriculture and food supply, but growing them is not easy. They are very sensitive to the environment. Even small changes in temperature or humidity can quickly cause pest outbreaks or plant disorders. The current way farmers manage this is through manual checking, working through the field, and inspecting plants by hand. This is slow, tiring, and often subjective. By the time a disease is spotted, the damage is already done. This leads to two problems. They are lost because the disease is caught too late. Too many pesticides because farmers spray chemicals that to be safe even when it may not be needed. So the core question is, can we build a smarter system that detects disease early and gives farmer clean advice on what to do? What is exactly what our system does? Our approach has three main components: agronomic data modeling, defining the safe environmental ranges for these crops. Second, zoonotic disease detection, an AI model that identifies disease from crop images. Three, drug advisory pipeline, an intelligent system that gives farmers route inspect level advice. Let me walk you through each one. First, we set up the environmental rules for the crops. We study agricultural literature and define the safe ranges for key parameters. For example, air temperature should be between 15 and 21. Above 27 causes premature flowering. Humidity should stay between 85 and 95%. If it drops below 70%, the plants start to wilt. Soil pH should be 6 to 6.8. If pH drops below 5.5, the plant becomes highly vulnerable to a disease called club root. These thresholds are programmed into our IoT sensors. When the value goes out of the safe range, the system sends an automatic order to the farmer before any visible symptoms appear. This is how we reduce diagnostic latency. The second component is our visual detection model, YOLO version 10. We chose YOLO version 10 because it is fast and accurate. It can detect a small disease spot as small as 5 to 10 millimeters. The model has three key parts. The backbone filters out background noise like soil or flattish mulch and focuses on lesion touches on the leaves. The net allows the model to detect disease spots of different size, from tiny necrotic spots to large infected patches. The head precisely locates and classifies the disease area even when leaf shapes are irregular. The model is designed for early anomaly detection. It flags that something is wrong Then the net component gives the detailed explanation. The third component is our RAG-based advisory system. RAG stands for Retrieval Augmented Generation. Think of it this way. After Zolo detects a disease, the farmer still needs to know what to do. A generic chatbot might give wrong or hallucinated advice. Our system is different. It works in three steps. 1. Extract. We convert the crop image into a compact digital representation using a lightweight model called EfficientNet. The next step is retrieve. We share a database of over 1,050 expert verified agricultural records to find the most relevant cases. The final step is generate. We pass that retrieved content through a language model to generate a structured response, diagnosis, reasoning, and a treatment plan. The key advance is that our recommendations are grounded in verified data, not guesswork. This makes the advice trustworthy for farmers. Here is how everything connects together. IoT devices in the field continuously collect images and environmental data, temperature, humidity, soil nutrients, and pH. Images are sent through the Zolo model for detection. Sensor data is stored in the database and used for threshold alerts. When a farmer wants more detailed advice, they can also manually submit an image with a description, and the RAG system will respond with actionable recommendations. The whole system runs on the cloud using AWS with a model and website dashboard for farmers to monitor their crops in real time. Now let me share our results. For the reduction model, we trained and tested on 2,659 images of disease leaves. The results are strong. Overall accuracy with 88.7%, MAP with 91.6%. This is the standard measure for detection quality. Inference time only 42 milliseconds per image, which is 24 frames per second. The model detects disease areas with a recall of 90.8%, meaning it rarely misses a disease even in challenging lighting or angles. For the advisory system, we test using a set of 500 expert level queries paired with verified diagnosis and treatments. Diagnostic alignment is 85%, meaning in 85 out of 100 cases, the system correctly identified the disease. Advisory relevance is 88.5%. The treatment advanced match expert recommendations globally. Response time is 2.3 seconds, fast enough for practical farm use. We also compare our system against two baselines against existing system. Ours is the only one that combines IoT sensing, visual detection, real-time alert, orders, actionable advisory, and traceability, all in one framework. When we compare the RAG approach against using a poor language model with no retrieval, the poor LLM had the hallucination rate of 18.5%. It sometimes inverts wrong chemical dosages. Our RAG system revealed that just 2.1%. This completes that grounding the AI in verified data is essential for safety critical applications like agriculture. To summarize, our system makes three key contributions. It bridges the gap between invisible sensor data and visible disease symptoms, giving farmers one unified picture. It eliminates latency, replacing slow manual checks with automated real-time monitoring. It restores trust through QA-based traceability. Consumers can scan a QA code and see the full farming history of what they buy. For future work, we plan to improve performance in low light conditions, expand the disease dataset using federated learning across multiple farms, and develop offline advisory using smaller content language models for edge devices. Ultimately, we believe this system is a practical step toward data-driven, sustainable agriculture. Thank you very much for your attention. I'm happy to take any questions. Our team contact is available in the paper. We welcome collaboration, especially with researchers working on smart farming or edge AI. Thank you.